Welcome to For Science Salah Lotfy channel, where science meets curiosity. في هذه القناة لا نكتفي بعرض الأبحاث العلمية، بل نترجمها إلى المعرفة التي تصل إليك أينما كنت. Our mission is to make global scientific research understandable, accessible, and multilingual. جميع الفيديوهات العلمية هنا مترجمة إلى اللغة العربية، بالإضافة إلى لغات عالمية أخرى. French, Spanish, German, Urdu, and more. Because science speaks every language. نعم، العلم يتحدث بكل اللغات، ونحن نحرص أن يصلك بلغتك. If you're passionate about science, you're in the right place. اشترك الآن وابدأ رحلتك مع العلم خطوة بخطوة. For Science Salah Lotfy channel, العلم للجميع.
Welcome to For Science Salah Lotfy channel. Today we explore an innovative piece of research that combines nanotechnology, natural products, and radiation science to create a new generation of wound healing dressings. Wound healing is a complex biological process. It passes through 4 overlapping stages: hemostasis, where bleeding stops; inflammation, when the body fights infection; proliferation, new tissue and blood vessels form; and finally, remodeling, where collagen strengthens the healed tissue. But treating wounds effectively remains a challenge, especially when infections occur or when healing is slow, like in diabetic wounds. This study introduces hydrogel dressings, soft, water-rich polymer networks that keep the wound moist, absorb fluids, and do not stick to the skin. The team developed hydrogels made from polyvinyl alcohol, PVA, a synthetic polymer with strength and flexibility; pectin, a natural polymer from fruit peels known for its anti-inflammatory action. To enhance healing, they incorporated silver-doped zinc oxide nanoparticles, AgZNO-NPs, with strong antibacterial activity, and lavender oil, a natural essential oil with soothing, antioxidant, and wound-healing properties. What makes this research even more fascinating is the use of electron beam irradiation. Instead of chemical cross-linking, electron beams were used to bind and sterilize the hydrogel in a single, eco-friendly step. This method ensures safety, eliminates toxic residues, and makes the dressings ready for direct medical use. The results were remarkable. The hydrogel showed strong antibacterial activity against Staphylococcus aureus, E. coli, Pseudomonas aeruginosa, and even the fungus Candida albicans. The dressings significantly inhibited biofilm formation, one of the toughest defenses bacteria use to survive. In rat models, wounds treated with hydrogels enriched with 5% lavender oil healed faster, with reduced inflammation, enhanced collagen formation, and better blood vessel growth. From a pharmaceutical and medical perspective, these findings are highly valuable. The dressings act as antimicrobial barriers, preventing infections. They provide a safe and biocompatible treatment with minimal blood cell damage. They accelerate tissue repair, making them promising for burns, chronic wounds, and post-surgical recovery. And here lies the crucial role of radiation science. The electron beam technology not only forms the hydrogel, but also sterilizes it in one step. This highlights how nuclear and radiation research can directly contribute to healthcare innovations. This research shows how combining nanoparticles, natural oils, and radiation technology can lead to safer, more effective wound treatments. It represents a promising step towards next-generation medical dressings. You've been watching For Science Salah Lotfy channel. Stay with us for more insights into the latest scientific breakthroughs shaping our future. Welcome to For Science Salah Lotfy channel. In today's episode, we highlight a recent research article published in the International Journal of Biological Macromolecules, Volume 288, 2025. The paper is titled, Rat Model Evaluation for Healing, Promoting Effectiveness and Antimicrobial Activity of Electron Beam Synthesized Polyvinyl Alcohol Pectin, Silver-Doped Zinc Oxide Hydrogel Dressings Enriched with Lavender Oil. This article was received on July 1, 2024, revised on November 18, 2024, and accepted on December 8, 2024. It became available online on December 11, 2024. This innovative work was carried out by a distinguished team from the National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt. The research team includes Dr. Nehad Ahmed, Polymer Chemistry Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt; Dr. Fouad Elshahawy, Polymer Chemistry Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt; Professor Dr. Amany Ismail Raafat, Polymer Chemistry Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt. Dr. Fatma Yehia Abdou Hamid, Lecturer of Pharmacology and Toxicology, Drug Radiation Research Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt. Dr. Hadeer Abdelfattah Taher, Lecturer of Microbiology, Drug Radiation Research Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt. The study addresses one of the most critical challenges in medicine: effective wound healing. Wound repair is a complex process involving hemostasis, inflammation, tissue proliferation, and finally remodeling. But in cases such as chronic wounds or burns, traditional treatments often fail to deliver rapid and infection-free recovery. To overcome this, the researchers designed hydrogel dressings based on polyvinyl alcohol, PVA, a synthetic polymer known for its mechanical strength, pectin, a natural polymer with anti-inflammatory properties, reinforced with silver-doped zinc oxide nanoparticles, Ag-ZNO-NPs for antimicrobial action, and enriched with lavender oil, a natural essential oil with antioxidant and healing effects. What makes this study unique is the use of electron beam irradiation as the method to synthesize and sterilize these hydrogels. This eco-friendly technology avoids harmful chemicals, achieves efficient cross-linking, and sterilizes the dressing in a single step, making it safe for medical use. The results were impressive. The dressings showed strong antibacterial activity against Staphylococcus aureus, E. coli, Pseudomonas aeruginosa, and even the fungus Candida albicans. They significantly inhibited biofilm formation, a key survival strategy of harmful microbes. In animal experiments using rat models, wounds treated with hydrogels containing 5% lavender oil healed faster, with reduced inflammation, enhanced collagen deposition, and increased blood vessel growth. From a medical and pharmaceutical perspective, these findings are groundbreaking. The dressings act as antimicrobial barriers preventing wound infections. They are biocompatible and safe, showing very low blood cell damage. They accelerate tissue regeneration, making them promising candidates for treating burns, chronic wounds, and surgical recovery. This research demonstrates how nanotechnology, natural oils, and radiation science equipment can come together to produce a next-generation wound dressing. It is a powerful example of how nuclear and radiation research in Egypt is contributing directly to healthcare innovations. You've been watching For Science Salah Lotfy channel. Stay tuned as we continue to bring you the latest scientific breakthroughs that shape our future. Welcome to For Science Salah Lotfy channel. In this episode, we explore an exciting piece of research focused on advanced wound healing dressings, a field where nanotechnology, natural products, and radiation science converge to solve medical challenges. Wound healing is a vital biological process divided into 4 overlapping phases: hemostasis, where bleeding stops; inflammation, when immune cells fight infection; proliferation, during which granulation tissue, collagen, and blood vessels form; and finally, remodeling, when the tissue matures and scars stabilize. Although medicine has developed many wound care strategies, such as ointments, polyurethane dressings, and hydrogels, these treatments are often costly and slow to act. This is where hydrogel technology comes in. Hydrogels are 3-dimensional polymer networks that absorb fluids, keep wounds moist, and allow oxygen flow. They do not stick to the wound, making dressing changes painless. In this study, researchers combined polyvinyl alcohol, PVA, a synthetic non-toxic polymer with strong swelling and mechanical stability, with pectin, a natural polymer from citrus peels, known for its biocompatibility and anti-inflammatory properties. Together, they form a hybrid hydrogel dressing with improved performance. To enhance the dressing's effectiveness, the team incorporated 2 key bioactive agents: silver-doped zinc oxide nanoparticles, Ag-ZNO-NPs, known for their antimicrobial power, and lavender oil, LVO, a natural essential oil with analgesic, antioxidant, and wound healing effects. The Ag-ZNO nanoparticles were synthesized using the precipitation method and characterized by XRD, FATEIR, and EDX. Transmission electron microscopy revealed their spherical shape with an average size of 27.4 nanometers. What makes this research unique is the use of electron beam irradiation to prepare the dressings. This clean technology allows both cross-linking and sterilization in a single step, without leaving residues, using chemicals, or requiring further purification. By increasing the PVA to pectin concentration up to 30%, the gel content reached 92%. Swelling capacity, crucial for absorbing wound fluids, peaked at 1,674% with 80% pectin content. However, raising the irradiation dose to 45 kGy increased the gel fraction but reduced swelling capacity. When Ag Xeno and Peas and lavender oil were added, the dressings showed slight decreases in swelling and gel fraction, but overall demonstrated 87% porosity and excellent fluid absorption. In pseudo-extracellular fluids, hydrogels with 10% lavender oil swelled to 419%, with a water vapor transmission rate of 271.1 gm2/H, values ideal for maintaining a moist wound environment. The real proof came from animal experiments. In rat excisional wound models, these lavender oil Ag/Xeno PVA pectin hydrogels showed high biocompatibility, strong antimicrobial potential, and remarkable wound healing capacity confirmed through histological and biochemical studies. They accelerated tissue granulation, promoted collagen replacement, enhanced wound contraction, and upregulated healing markers, making them strong candidates for clinical wound healing applications. This research shows how nanotechnology, natural polymers, essential oils, and radiation technology can be integrated into a powerful biomedical solution. These advanced hydrogel dressings have the potential to transform wound care, especially for burns and chronic injuries. You've been watching for Science Salah Lotfy channel. Stay with us as we continue to uncover scientific innovations shaping the future of healthcare. Welcome to For Science Salah Lotfy channel. Today we will dive deeper into the materials, methods, and experimental procedures behind an innovative study that developed nanocomposite hydrogel dressings for wound healing, combining polyvinyl alcohol, pectin, silver-doped zinc oxide nanoparticles, and lavender oil. At the heart of this research lies a meticulous selection of materials, each chosen for its unique properties and synergistic potential to create a sophisticated, multifunctional platform for active wound healing. The hydrogel's foundation is polyvinyl alcohol, or PVA, with a molecular weight of 14,000 G per mole. This polymer was selected for its exceptional biocompatibility and non-toxic nature. Its excellent film-forming ability creates a flexible, protective barrier, while its structure absorbs wound exudate, maintaining a moist environment crucial for healing and ensuring patient comfort. Complementing the PVA is pectin, a natural polysaccharide from plants, with a molecular weight of 50,000 G per mole. Pectin brings its own therapeutic benefits, being biodegradable and known to actively promote cell adhesion and proliferation. Its natural gelling properties work in concert with PVA to establish the hydrogel's structural integrity and ideal texture. The primary active ingredient is lavender oil, or LVO, renowned for its potent antimicrobial and anti-inflammatory effects. To integrate this oil into the water-based hydrogel, researchers used Tween80. This non-ionic surfactant acts as an emulsifier, dispersing the lavender oil into microscopic droplets. This creates a stable emulsion, ensuring the oil is evenly distributed and readily available to exert its therapeutic effects across the entire wound bed. To amplify the antimicrobial power, the design incorporates metallic nanoparticles. High-purity zinc nitrate hexahydrate and silver nitrate, both of 97% purity, served as precursors. These were used to synthesize zinc oxide and silver nanoparticles. Zinc oxide offers antibacterial and regenerative properties, while silver nanoparticles provide potent, broad-spectrum antimicrobial action, crucial for combating infection and preventing biofilm formation. Precise environmental control was essential. Sodium hydroxide and hydrochloric acid were used to meticulously adjust pH during synthesis, a critical factor for both nanoparticle formation and hydrogel cross-linking. Additionally, phosphate salts were used to prepare a phosphate-buffered saline solution, which mimics the body's physiological conditions for all subsequent in vitro testing, ensuring clinically relevant results. The sourcing of materials highlights the study's clinical focus. High-quality lavender oil was procured from Cairo, Egypt. Most critically, the microbial strains for testing were not lab cultures. They were obtained directly from wound patients at the Nassar City Health Insurance Hospital. This ensures the dressing was challenged with real-world pathogens, making the study's findings profoundly more meaningful for actual patient care. The National Center for Radiation Research and Technology, NCRRT, part of the Egyptian Atomic Energy Authority, provided the electron beam irradiation facility. The accelerator operated at 3 MeV, with a beam current of 10 or 3 Ma, and a scanning velocity of 3.39 meters per minute. This irradiation technology was used to cross-link polymers into hydrogels, and simultaneously sterilize the samples, an eco-friendly process with no chemical residues. The synthesis of our silver-doped zinc oxide nanoparticles, or AgZno-NPs, was accomplished using the chemical precipitation method. This technique is highly favored for its simplicity and precise control over particle size and composition. The process began by preparing the precursor solution. We dissolved zinc nitrate hexahydrate, our zinc source, and silver nitrate, our dopant source, into high-purity deionized water. Using deionized water is essential to avoid contamination from extraneous ions. The solution was stirred continuously to form a clear, homogeneous, aqueous solution, setting the stage for precipitation. Next, a sodium hydroxide solution was introduced as the precipitating agent. It was added drop-wise into the precursor solution, a critical step for ensuring uniform nucleation and growth, which leads to a consistent nanoparticle size. Throughout this addition, the reaction was maintained at a constant temperature of 60 degrees Celsius and a pH of 8.5. The temperature governs the reaction rate, while the specific pH promotes the formation of zinc hydroxide and the incorporation of silver. As the base was added, a milky white precipitate of silver-doped zinc hydroxide instantly formed. After the reaction, this precipitate underwent extensive purification. It was washed repeatedly with deionized water to remove byproducts, then separated via centrifugation. The purified solid was then dried in an oven at 80 degrees Celsius to remove all moisture. The final step was calcination, where the dry powder was heated in a furnace to 350 degrees Celsius. This crucial thermal process converts the zinc hydroxide into crystalline zinc oxide and permanently locks the silver atoms into the ZNO crystal structure, yielding the final, fine AgZno nanopowder. To confirm the success of our synthesis, we performed a comprehensive characterization of the nanopowder. X-ray diffraction or XRD analysis confirmed the material possessed the hexagonal Wurtzite crystal structure of ZNO. Furthermore, slight shifts in the XRD peak positions provided strong evidence that silver ions were successfully incorporated into the ZNO lattice. Fourier transform infrared spectroscopy, or FTIR, verified the chemical composition by detecting the characteristic ZNO bond and confirming the absence of impurities. To visualize the nanoparticles directly, we used transmission electron microscopy, or TEM. The TEM images revealed uniformly distributed spherical nanoparticles with an average diameter of about 27 nanometers. Finally, energy dispersive X-ray spectroscopy, or EDX, provided an elemental map, confirming the presence and distribution of zinc, oxygen, and silver throughout the sample. Together, these results provided a complete picture, validating the successful synthesis of our target AgZno nanoparticles. Hydrogels were prepared from PVA and pectin mixtures at different concentrations, 10, 20, and 30 Wt%, exposed to irradiation doses of 25, 35, and 45 kGy. For nanocomposites, 310 Wt% of AgZno was mixed into a 70, 30 PVA PET solution. The best-performing hydrogel contained 7 Wt% AgZno irradiated at 35 kGy. For final wound dressings, different concentrations of lavender oil, 1%, 5%, and 10% were added, producing LVO, PVA PET, AgZno nanocomposite hydrogels. To simulate wound exudates, researchers prepared pseudo-extracellular fluid, PCF, a solution mimicking the ionic composition of real wound fluids. Optimization studies showed increasing polymer concentration improved gel fraction to 92%. Pectin content increased swelling up to 1,674%. Higher irradiation doses boosted gel strength but reduced swelling capacity. Characterization included porosity, up to 87%, ensuring oxygen flow and fluid absorption. Swelling and PCF uptake, dressings with 10% lavender oil reached 419% swelling capacity. Water vapor transmission rate, WVTR, 271 gm2h, ideal for wound moisture balance. To validate the hydrogel's antimicrobial efficacy, we tested it against a panel of clinically relevant microorganisms. These represent the most common culprits in wound infections. We targeted gram-positive bacteria like Staphylococcus aureus, a notorious cause of skin infections, and the resilient Bacillus subtilis. We also challenged it with gram-negative bacteria, whose outer membrane often confers higher resistance. For this we used Pseudomonas aeruginosa, a major threat in chronic wounds, and Escherichia coli. Finally, to ensure broad-spectrum activity, we included the fungal pathogen Candida albicans, which can complicate healing. An effective dressing must combat this diverse array of threats. Using the agar disc diffusion method, hydrogel samples were placed on plates seeded with each microbe. The results were visually striking. Clear zones of inhibition, areas where microbial growth was completely halted, formed around each sample as antimicrobial agents diffused from the hydrogel. The consistent size of these zones across all tested pathogens provided the first powerful confirmation of the dressing's broad-spectrum antimicrobial potential, demonstrating its ability to neutralize bacteria and fungi on contact. But how does the hydrogel achieve this? To uncover the mechanism, we performed further assays. First, a protein leakage test confirmed the hydrogel actively punctures and disrupts bacterial membranes, causing their vital contents to spill out. This is a primary mode of its killing action. Next, we addressed the critical challenge of biofilms, slimy, fortress-like bacterial communities that are highly resistant to antibiotics. A biofilm inhibition assay revealed the hydrogel could suppress their formation by an impressive 70 to 80%. This preventative capability is crucial for stopping persistent infections. Furthermore, growth curve analysis, which tracks bacterial population over time, showed that the hydrogel significantly slowed the exponential growth of bacteria like B. subtilis, demonstrating a powerful bacteriostatic effect that puts the brakes on microbial proliferation. For definitive proof, we used scanning electron microscopy, or SEM, to see the physical aftermath. Before exposure, SEM images showed healthy bacterial cells with smooth surfaces. After interacting with the hydrogel, the picture was dramatically different. The cells were shrunken, wrinkled, and their membranes clearly ruptured. This direct visual evidence of morphological destruction provides a powerful microscopic confirmation of our other findings. The hydrogel doesn't just inhibit microbes, it physically dismantles them, affirming its status as a robust and multifaceted antimicrobial agent ready for the challenges of wound healing. Both in vitro and in vivo tests confirmed safety. Hemolysis tests showed very low red blood cell damage. Animal studies on female Wistar rats demonstrated excellent wound closure rates. Wounds were created on the dorsal skin of rats and treated daily for 14 days. Groups included untreated controls, gauze with Vaseline, plain hydrogels, and nanocomposites enriched with lavender oil. Findings: rats treated with 5% LVO-Ag-Xeno PVA PET hydrogels showed the fastest wound closure. Histological analysis revealed granulation tissue formation, collagen replacement, angiogenesis, and reduced inflammation. Biochemical tests showed increased VGF, vascular endothelial growth factor, and TGF-B, critical for angiogenesis and tissue regeneration. Elevated ASMA, indicating active tissue remodeling, reduced MDA, lipid peroxidation marker, and enhanced antioxidant defenses, GSH and GST. This comprehensive study demonstrates how combining synthetic and natural polymers, nanoparticles, lavender oil, and radiation science can yield advanced wound dressings with remarkable antimicrobial, biocompatible, and healing properties. These results highlight the power of radiation technology in biomedical innovation and its potential impact on clinical wound management. You've been watching For Science Salah Lotfy channel. Stay tuned as we continue to explore the science shaping the future of healthcare. Welcome to For Science Salah Lotfy channel. In this episode, we continue exploring the fascinating research on nanocomposite hydrogel dressings, reinforced with silver-doped zinc oxide nanoparticles and lavender oil. Today, we focus on the results and discussion section where the true performance of these advanced wound dressings is revealed. The Ag-Xeno nanoparticles were carefully analyzed. XRD patterns confirmed their crystalline structure, revealing distinct peaks that correspond to the hexagonal Wurtzite phase of ZNO, and additional peaks showing the presence of silver within the lattice. The average crystallite size was calculated at around 26-27 nanometers. FTIR spectra confirmed the interaction between silver and zinc oxide bonds, while TEM images revealed spherical nanoparticles with uniform sizes. EDX mapping confirmed their composition, showing atomic percentages of 42.8% zinc, 52.1% oxygen, and 5% silver. This confirms that silver was successfully doped into the ZNO lattice, enhancing both structural and antimicrobial properties. When electron beam irradiation was applied to aqueous solutions of polyvinyl alcohol and pectin, active species such as hydroxyl radicals and hydrogen peroxide were generated through water radiolysis. These radicals abstracted hydrogen atoms from the polymer chains, producing macroradicals that recombine to form a cross-linked hydrogel network. This method enabled the incorporation of Ag-Zeno nanoparticles and lavender oil directly into the polymer matrix, creating a stable, sterilized, and functional dressing in one step. The gel fraction, a measure of cross-linking efficiency, increased with higher polymer concentrations and irradiation doses, from 32% at 25 kGy to 92% at 45 kGy. Increasing polymer concentration from 10% to 30% also raised gel fraction from 85% to 92%. However, introducing more pectin reduced gel fraction due to chain scission during irradiation. Adding Ag-Zeno nanoparticles also lowered the gel content, dropping from 91% to 33% when nanoparticle loading reached 10%. Similarly, adding lavender oil slightly reduced gel fraction because some of its bioactive compounds absorbed part of the radiation dose. The swelling capacity is crucial for wound dressings. Hydrogels with higher polymer content absorbed more fluid. Pectin-rich hydrogels swelled up to 1,674% due to its hydrophilic groups. But increasing irradiation dose reduced swelling, since tighter cross-linking restricted water entry. When Ag-Zeno nanoparticles and lavender oil were added, swelling decreased. For example, with 10% nanoparticles, swelling dropped to 340%. With 10% lavender oil, swelling reached about 815% compared to over 1,600% in plain hydrogels. This reduction is linked to the hydrophobic nature of lavender oil and the compacting effect of nanoparticles. FTIR confirmed the chemical bonds in the hydrogel matrix. New peaks appeared with Ag-Zeno, while lavender oil caused slight spectral shifts, proving its integration into the network. SEM images revealed plain PVA pectin hydrogels had fluffy networks with small pores. Adding Ag-Zeno nanoparticles made the structure denser with reduced porosity. Lavender oil further compacted the network, giving thicker boundaries and fewer pores. Porosity decreased from 94% in plain hydrogel to just 67% when 10% lavender oil was added. The ability to absorb wound exudates was tested using pseudo-extracellular fluid. Plain hydrogels absorbed up to 709%, with lavender oil absorbance decreased, 618% for 1% LVO, 486% for 5% LVO, and 419% for 10% LVO. Water vapor transmission rate, WVTR, is another critical property. The plain hydrogel recorded 394 gm2IH within the optimal healing range. Ag-Zeno reduced it slightly, while 10% lavender oil lowered it further to 271 gm2SH. This ensures moisture balance, not too dry, not too wet. The dressings were tested against bacteria and fungi. Staphylococcus aureus, Bacillus subtilis, E. coli, Pseudomonas aeruginosa, and Candida albicans. The results were impressive. Dressings with 5% lavender oil showed the strongest antimicrobial effect, with inhibition zones reaching 31 mmM against Bacillus subtilis. The synergy between Ag-Zeno nanoparticles and lavender oil amplified the antibacterial effect by disrupting membranes, generating reactive oxygen species, and preventing cell division. Biofilm formation is a major obstacle in chronic wound healing. The 5% LVO Ag-Zeno hydrogel inhibited biofilm formation significantly, up to 69.5% inhibition for Bacillus subtilis, between 56% and 65% for other strains including S. aureus and C. albicans. Lavender oil disrupts bacterial membranes, while Ag-Zeno prevents adhesion, stopping biofilm development at its early stages. Together, these results prove that LVO, PVA PET, Ag-Zeno Nanocomposite Hydrogel dressings combine the mechanical strength of synthetic polymers, the hydrophilicity of pectin, the antimicrobial action of silver-doped ZNO, and the healing boost of lavender oil. They maintain optimal moisture, fight pathogens, prevent biofilms, and accelerate tissue regeneration. This makes them strong candidates for next-generation wound care solutions. Thank you for watching for Science Salah Lotfy channel. Stay with us as we continue to uncover the science behind tomorrow's medical innovations. For Science Salah Lotfy channel. Today, we continue exploring the fascinating journey of nanocomposite hydrogel dressings reinforced with lavender oil and silver-doped zinc oxide nanoparticles. In this part, we dive into the antimicrobial mechanisms, biocompatibility tests, and in vivo wound healing results, the most important evidence for their medical potential. To truly understand if an antimicrobial agent is effective, we need to look for definitive evidence of cellular damage. One of the most compelling and direct indicators of bactericidal action is the measurement of protein leakage. A bacterium's cell membrane acts as a vital gatekeeper, meticulously controlling what enters and exits the cell. It maintains the delicate internal environment, or cytoplasm, which is packed with essential proteins and enzymes. When this barrier is breached, it's a catastrophic event for the organism. The uncontrolled release of these crucial intracellular components is a clear sign that the cell's structural integrity has been fatally compromised. To quantify this effect, we conducted a protein leakage assay using Bacillus subtilis. Cultures of the bacteria were incubated under controlled conditions. One group was treated with our Nanocomposite Hydrogel containing 5% lavender oil, while a control group was incubated with a plain hydrogel. After incubation, the supernatant was collected and analyzed using a spectrophotometric method to measure protein concentration. The results were striking. The control group showed only a negligible baseline protein release. In contrast, the bacteria exposed to the 5% lavender oil hydrogel released a substantial 260 micrograms per milliliter of protein. This massive efflux of protein directly confirms that lavender oil disrupts the bacterial cell membrane. But how does this happen at a molecular level? The primary components of lavender oil, such as linalool and linaloyl acetate, are lipophilic. They are drawn to the phospholipid bilayer of the bacterial membrane. These oil molecules insert themselves into the lipid structure, disrupting its orderly arrangement. This intercalation increases the membrane's fluidity and permeability, creating pores and causing widespread destabilization. The membrane loses its ability to function as a selective barrier, leading to the leakage of vital cytoplasmic contents and ultimately cell death. Furthermore, our investigation revealed a clear relationship between the concentration of lavender oil and the extent of membrane damage. We tested a range of concentrations from 1% up to 5%. As visualized in this graph, the effect is strongly dose-dependent. At lower concentrations, we observed a moderate increase in protein leakage compared to the control. However, as the concentration of lavender oil within the hydrogel was increased, the amount of protein leakage escalated significantly. This demonstrates that a higher concentration of the active agent leads to more extensive membrane disruption. This powerful quantifiable evidence solidifies the mechanism by which our lavender oil-infused hydrogel eradicates harmful bacteria, paving the way for its clinical application. To quantify the hydrogel's antibacterial efficacy over time, researchers conducted a growth kinetics analysis. This tracks the population growth of bacteria in a liquid culture. The model organism was a gram-positive bacterium common in wound infections, making it a clinically relevant target. Growth was monitored by measuring the optical density, or OD, of the culture at 600 nanometers. At this wavelength, light is scattered by the bacterial cells, so a higher OD value corresponds to a higher concentration of bacteria, providing a precise measure of population dynamics. First, a control group was established within a nutrient-rich broth, but no treatment. As expected, these bacteria exhibited a classic sigmoidal growth curve, starting with a lag phase for adaptation, followed by a rapid exponential growth phase, and finally leveling off into a stationary phase. The untreated control group reached a peak optical density of 2.0, indicating a dense, thriving bacterial population. This result served as the critical baseline, representing maximum potential growth against which the hydrogel's performance would be measured. The results from the treated group were strikingly different. When was cultured with the hydrogel containing 5% lavender oil, its growth was almost completely halted. The growth curve remained nearly flat, and the final optical density was a mere 0.125. Compared to the control's OD of 2.0, this represents a staggering 93.75% inhibition of bacterial growth. Such a profound reduction suggests the hydrogel has a potent bactericidal action, actively killing the bacteria, which is essential for effectively clearing an infection. This powerful bactericidal activity stems from a multi-pronged attack. A primary mechanism is the generation of reactive oxygen species, or ROS, by the silver-zinc oxide nanoparticles. These highly unstable molecules, like superoxide and hydroxyl radicals, wreak havoc inside the cell. They attack bacterial DNA, causing strand breaks that halt replication. They also target proteins, causing them to misfold and lose function, shutting down essential enzymes. Furthermore, ROS initiate lipid peroxidation in the cell membrane, compromising its integrity. Simultaneously, the nanoparticles release positively charged silver and zinc ions. These ions are drawn to the negatively charged bacterial membrane, where they disrupt its electrical potential and interfere with cellular respiration, leading to fatal damage. Finally, the lavender oil plays a crucial role, working with the nanoparticles to create a powerful synergistic effect, where the combined action is far greater than the sum of their individual effects. The active compounds in lavender oil, such as linalool, are known to disrupt bacterial membranes, making them more permeable. This initial damage likely allows the reactive oxygen species and metal ions to penetrate the bacterial cell more easily, amplifying their lethal impact. This multi-target strategy is a significant advantage, as it makes it exceedingly difficult for bacteria to develop resistance compared to conventional single-target antibiotics. Scanning electron microscopy, (CM), provided direct visual evidence. Control bacteria appeared healthy, with smooth, intact surfaces. But after treatment with the Elvio-Ag-Xeno hydrogel, the cells showed deformation, wrinkling, ruptures, and content leakage. Some bacteria were even partially lysed, with nanoparticles observed attached to their surfaces. This confirmed the physical disruption of bacterial structures, in line with the protein leakage and growth curve findings. A key requirement for medical dressings is blood compatibility. Hemolysis tests showed that all hydrogel samples were within the safe range. The plain hydrogel caused about 3% hemolysis, while the lavender oil and nanoparticle composites showed even lower values, around 1 to 2%. Since hemolysis below 5% is considered safe, these dressings are clearly biocompatible and non-toxic to red blood cells. With promising in vitro results, the next critical step was evaluating the hydrogels in a living system. Animal studies using a full-thickness wound model in rats provided the definitive test of their healing power. This in vivo setting allows observation of the complex interplay between cellular activity, tissue regeneration, and the inflammatory response defining the wound healing cascade. To establish a baseline, we examined the control groups. Histopathological analysis of untreated wounds revealed extensive necrotic tissue and a disorganized cellular environment. Standard gauze-treated wounds fared no better, showing severe, prolonged inflammation. Microscopically, these samples were flooded with inflammatory cells, indicating a stalled healing process with virtually no new collagen formation. Applying a plain hydrogel offered a slight improvement by maintaining a moist environment, supporting some cellular migration. The real advancement came with the Nanocomposite Hydrogel containing silver and zinc oxide. These nanoparticles exerted a powerful antimicrobial effect, reducing the wound's bacterial load. This allowed the body's repair mechanisms to take hold, resulting in noticeable epidermal regeneration and initial collagen deposition. But the most impressive results emerged from the hydrogel with 5% lavender oil. Building on lavender's known anti-inflammatory and pro-collagen properties, this concentration unlocked a synergistic effect with the hydrogel scaffold, accelerating healing to an unprecedented degree. A detailed look at the tissue sections revealed a remarkable story of regeneration across 4 key areas. First, complete epidermal regeneration. Unlike the thin, incomplete layers in other groups, the 5% lavender oil hydrogel promoted a thick, well-structured epidermis. It was complete with distinct basal, spinous, and granular layers, and a fully formed, keratinized outer layer. This was the reconstruction of a functional skin barrier. Second, minimal inflammation. The lavender oil actively modulated the inflammatory response, promoting a rapid transition to the proliferative healing phase. Histology showed a significant reduction in neutrophils and a shift towards M2 macrophages, the pro-resolution phenotype essential for tissue repair, creating a microenvironment conducive to healing. Third, strong, healthy granulation tissue formation. This new tissue filling the wound space was dense and highly vascularized. We observed robust angiogenesis, the formation of new blood vessels, critical for supplying oxygen and nutrients. The tissue was packed with active fibroblasts, the cellular engines building the new extracellular matrix, and finally, the quality of the new matrix. The hydrogel guided the deposition of mature, thick collagen fibers, perfectly aligned in a basket weave pattern that mimics healthy dermis. This is the key difference between true regeneration and simple scarring, resulting in tissue that is not only healed, but also strong and flexible. Interestingly, this demonstrates a clear dose dependency. The 10% lavender oil formulation was significantly less effective, not due to toxicity, but a physical limitation. The excess hydrophobic oil interfered with the hydrophilic polymer chains during cross-linking. This disruption hindered the formation of a stable, porous hydrogel network, compromising its structural integrity and ability to manage wound exudate. This impeded healing, highlighting the delicate balance between a bioactive payload and the scaffold's physical properties. The wound contraction data confirmed these findings. Across 14 days, control wounds contracted very slowly, while hydrogels accelerated healing. The 5% lavender oil group showed the highest wound contraction rates, outperforming even the silver-only group. This means the balanced combination of lavender oil and ag-xeno nanoparticles provides the optimal healing environment. From protein leakage to growth inhibition, from SEM images to animal healing studies, the evidence is clear. These LVO, PVA, PET, ag-xeno nanocomposite hydrogel dressings are antimicrobial, destroying pathogens at the cellular level, biocompatible, safe for human cells and blood, and therapeutically effective, accelerating wound closure and tissue regeneration. The 5% lavender oil formulation emerged as the best candidate for advanced wound care. Thank you for joining us on For Science Salah Lotfy channel. Stay tuned as we continue to explore cutting-edge research transforming healthcare and biotechnology. Welcome back to For Science Salah Lotfy channel. We now reach the final stage of our exploration into lavender oil silver-doped zinc oxide nanocomposite hydrogels and their role in wound healing. Let's focus on the concluding evidence from histology, oxidative stress analysis, and wound healing markers. Histological evaluations compared untreated wounds, gauze-treated wounds, and hydrogel-treated groups. Untreated and gauze wounds showed necrosis, inflammation, and minimal collagen. The ag-xeno hydrogels improved regeneration, with new blood vessels and collagen deposition, but the 5% lavender oil hydrogel stood out, showing full epidermal regeneration, minimal inflammatory cell infiltration, strong granulation tissue, and well-organized collagen fibers. Interestingly, the 10% lavender oil group was less effective, highlighting the importance of a balanced dose. Measurements of wound contraction over 14 days revealed significant improvements. The 5% lavender oil group achieved the highest contraction rate, faster than all other groups. Even though 10% lavender oil promoted healing, the contraction was less efficient than the 5% formulation. This confirms that moderate lavender oil concentration produces optimal results. The oxidative status of wound tissues was a key factor. MDA levels, a marker of oxidative stress, were significantly reduced in groups treated with 1% and 5% lavender oil hydrogels. At the same time, GSH activity, a natural antioxidant defense, was greatly increased, while GST enzyme activity decreased. This shows that lavender oil doesn't just fight infection, it also helps maintain the delicate balance of reactive oxygen species, ROS, needed for proper tissue repair. At the molecular level, the dressings boosted essential wound healing markers, VGF, the key protein for angiogenesis, TGF-B, which promotes fibroblast growth and collagen synthesis, and ASMA, vital for wound contraction. Once again, the 5% lavender oil hydrogel showed the strongest stimulation of these markers, confirming its superior role in accelerating healing. Altogether, this study demonstrates that lavender oil ag-xeno PVA pectin hydrogels fabricated using electron beam irradiation are safe and biocompatible, strongly antimicrobial, antioxidant, and anti-inflammatory, and clinically effective in accelerating wound healing. Among all tested formulations, the 5% lavender oil hydrogel emerged as the most promising candidate. This innovation highlights the power of combining natural essential oils, nanotechnology, and radiation science to design the next generation of wound care dressings. Thank you for watching For Science Salah Lotfy channel. Stay tuned for more scientific insights that connect advanced research with real-world healthcare solutions. As we reach the conclusion of today's episode on For Science Salah Lotfy channel, I would like to take a special moment to extend my heartfelt gratitude to the brilliant research team who made this work possible. Dr. Nehad Ahmed, Polymer Chemistry Department, National Center for Radiation Research and Technology, NCRRT, Egyptian Atomic Energy Authority, Cairo, Egypt. Dr. Fouad Elshahawy, Polymer Chemistry Department, NCRRT, Egyptian Atomic Energy Authority, Cairo, Egypt. Professor Dr. Amany Ismail Raafat, Polymer Chemistry Department, NCRRT, Egyptian Atomic Energy Authority, Cairo, Egypt. Dr. Fatma Yehia Abdou Hamid, lecturer in pharmacology and toxicology, Drug Radiation Research Department, NCRRT, Egyptian Atomic Energy Authority, Cairo, Egypt. Dr. Hadeer Abdelfattah Taher, lecturer in microbiology, Drug Radiation Research Department, NCRRT, Egyptian Atomic Energy Authority, Cairo, Egypt. I am Professor Dr. Salah Lotfy from the Egyptian Atomic Energy Authority, and it is my honor to recognize and thank these outstanding scientists for their remarkable contribution in advancing polymer chemistry and biomedical applications through radiation research. And of course, my warm thanks go to you, our viewers. Your continuous support of For Science Salah Lotfy channel gives life to this work. Please share your thoughts, questions, or reflections about this research in the comments below. Your engagement enriches the dialogue between researchers and the wider community. This concludes today's episode. Thank you for watching, and I look forward to meeting you again in our next scientific journey here on For Science Salah Lotfy channel.